Hi guys, so today I have a really fun problem for you, and this is a problem from the IOQM, and we're going to learn a little bit of number theory today. We're going to see how we can reduce equations mod n, a little bit about primitive roots and generating perfect squares. So let's begin.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students. Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions.
This was the problem number 13 from the Indian Olympiad qualified mathematics in 2021. This is actually a pretty nice problem. It's one of the harder problems on the test, and we're going to see how we can use elementary number theory in order to solve this. In this video, we are going to be learning how working and reducing equations mod n works. So how taking mod n works and what's the intuition behind reducing an equation mod n. Then we're also going to have a look at primitive roots modulo n. We're also going to look at generating perfect squares, and we're going to look at book suggestions with the IOQM. And at the end, we have a similar but challenging problem. Right? So we need to find all natural numbers n such that the modulus of 2 raised to the power n plus 5 raised to the power n minus 65 is a perfect square. Right? So this is an equation given to us, and this needs to be perfect. So how exactly are we supposed to work with this? Well, obviously it's a number theory problem. Most likely we're going to need some ideas of congruence modulo. So what you can basically see is that we have 5 raised to the power n and 65, which are both really multiples of 5. And if you know a little bit about primitive modulo, you can see that 2 is a primitive root mod 5. Right? So what does this mean? That basically means that there will exist an integer k, so that 2 raised to the power k is congruent to a mod 5 for all integers a crow prime to 5. That's basically what it means. Right? Now we can see that 2 is a primitive root mod 5. We have 5 raised to the power n, which will be a multiple of 5, and we have 65. So it's probably we kind of get the intuition that we will have to work mod 5. Right? Cool. So what I thought is maybe we can reduce this into a certain number of cases. The case 1 would be when 2 raised to the power n plus 5 raised to the power n minus 65 is less than 0. So that means the modulus was open as 65 minus 2 raised to the power n minus 5 raised to the power n. And this obviously happens for n is equal to 1 and 2. And because we only have two cases, we can check them by hand. And we can actually see that at n is equal to 1, we get the expression as 65 minus 2 minus 5, which is 58, which is not a perfect square. And at n is equal to 2, we get the expression as 65 minus 4 minus 25, which is 36, which is a perfect square. So n is equal to 2 is a valid solution. Right? So let's move on to the other case, case 2, where 2 raised to the power n plus 5 raised to the power n minus 65 is actually greater than 0. So the modulus opens in positive, right? Now this obviously happens at n greater than or equal to 3. And so we will have this expression 2 raised to the power n plus 5 raised to the power n minus 65 without the mod symbol. And if we just reduce this in mod 5, we will get this as 2 raised to the power n mod 5. Right? And yeah, so 2 raised to the power n mod 5. Now let's see what values they can have. So let's just make a table between n and 2 raised to the power n and see what values it will take. Now if you take n1, 2 raised to the power n mod 5 would be equal to 2, right? If we take n2, 2 raised to the power n mod 5 is 4. If we take n as 3, we will get 3. And if we take n as 4, we will get 1. And from Fermat's little theorem, we can see that this process, this cycle keeps on repeating. So if I have n is equal to 5, 2 raised to the power n mod 5 will be 2, and so on and so forth. The cycle will keep repeating. Now we can actually see that these are the only perfect squares mod 5. 1 and 4 in this case. Right, so these are the only perfect squares mod 5. So I can actually see that n is equal to 2 and n is equal to 4 give us a perfect square mod 5, right? So I can deduce that n needs to be equal to 2m. So n has to be even, basically. That's the crux of it. Why does n has to be even? Because we need a perfect square, right? And 1 and 4 the only perfect square 2 raised to the power n mod 5, right? So that basically means n is a perfect square. Now if n is equal to 2m, And we also saw that in this case n is greater than equal to 3, therefore we notice that m has to be greater than equal to 2. And again, I'm going to split this up into two cases, case A and case B. Case A, we are going to consider where m is equal to 2 and m is equal to 3. And in the next case, we're going to consider the scenario where m is greater than equal to 4. Okay. Now at m is equal to 2 and m is equal to 3, we can actually see that n will be 4 and n will be 6. And you can actually see that n is equal to 4 actually satisfies by just checking, and then n is equal to 6 does not satisfy. Okay, so I'll leave this to you to check out yourself. Now obviously we come on to the case B, and this is really where the crux of the problem is, where the problem is really interesting, right? Now what is the case B? Case B is nothing but m is greater than equal to 4, and since n was 2m, n has to be greater than equal to 8, right? Now I can write 2 raised to power n as 2 raised to power 2m, and that will be greater than equal to 2 raised to power 8, which is 128, right? Now 2 which is basically 128, right? Now if I just consider the given expression, what is the given expression? 2 raised to power n plus 5 raised to power n minus 65. Now if I just consider 2 raised to power n minus 65, will it be greater than 0 for n greater than equal to 8? Of course it will be, right? This is going to be greater than equal to 128 minus 65, which is obviously greater than 0, right? So 2 raised to power n minus 65 is greater than 0, so this expression will always be 5 raised to power n greater than that, right? So can I establish some sort of an inequality over here? And you'll actually see why I'm trying to do that. So I can actually write this term that we intend to find out if it's a perfect square or not. This will be less than 5 raised to power n, obviously, and which will be greater than 0, as all exponential functions are greater than 0. And this 5 raised to power n is nothing but 5 raised to power m whole squared, right, as n was 2m. So I can get this inequality on this side, and on the other side I can write this as this quantity is less than 25 raised to power m plus 4 raised to power m plus 1, right? And why I did this? Well, we can just transform this into something that we can work with. So we can write this as 5 raised to power n whole square. This will be less than plus 2 times 5 raised to power m plus 1. And you can actually see that the inequality still actually holds. And this is nothing but 5 raised to power m plus 1 whole square. So what can we see from here? We can actually see that 2 raised to power n plus 5 raised to power n minus 65 is less than 5 raised to power m plus 1 whole square, and at the same time 2 raised to power n plus 5 raised to power n minus 65 is greater than 5 raised to power m whole squared, right? Or in other words, 2 raised to power n plus 5 raised to power n minus 65 lies between two perfect squares, two consecutive perfect squares, right? If you take 5 raised to power m as t, you can see that this quantity lies between two perfect squares, and therefore this can never be perfect square. Therefore we have 0 solutions in this case, right? So therefore the only two solutions are n is equal to 2 and n is equal to 4, right? So yeah, that was the question that was given to us, and I really hope you enjoyed that. It was a pretty good problem. It was one of the more challenging problems in the tests, and we really had to work quite a bit in congruence modulo to solve this one. Okay, so coming on to certain book sessions for the IOQM, we have challenges in Tilde of pre-college mathematics, mathematical circles, excursion mathematics, a test of mathematics at 10+2 level, elementary number theory by David Burton, elementary theory of numbers by Sierpinski. We also have problem solving strategies by Arthur Engel and principles and techniques in combinatorics. Right, so at the very end I have a similar but challenging problem for you, and I want you to find all m comma n such that 2 raised to power m plus 3 raised to power n is a perfect square. So 2 raised to power n plus 3 raised to power n will be k square for some k, and m and n are natural numbers. And as always, if you make any progress on this question, if you're able to solve it, please let me know in the comment section below, and I'll get back to you. Until then, I'll see you later. Bye-bye.
The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR and IISc. For more information, visit cheenta.com.